So let's consider the following chart of information. Suppose we have a two-way chart, male, female, and then we have political preference, Democrat, Republican. Okay, it's a fictitious example. So this is a survey of 100 people, and here's what they had to say. Okay, all right, so that's a two-way table of gender compared to political preference. We can find the marginal distribution. So just to remind you of some old vocabulary, the marginal distributions are literally that. You add up to see what happens in the margins here. So if you add these two numbers, you get a total of 83 males that were surveyed. And then here, add those numbers, 17 females, for a total of 100. Let's get the marginal distribution with respect to party. That's what this would be. This is the marginal distribution of political party preference. Down here, this is the marginal distribution of gender. Okay. All right, so what do we have here? These numbers add to 60. So there were 60 Democrats that were surveyed and then 40 Republicans. Okay. So we can ask the typical questions. Like, for example, I could say, what's the probability that someone was a male and preferred the Democratic Party, right? So that's just saying, what's the probability male and Democrat? Well, you can see that right here. It's 47 of those in this category out of 100 total. Okay? And you could ask other questions as well. But now here's the question I'm really interested in. It's called a conditional probability. So here's how you might want to write it. So probability of male, given that we chose a Democrat. Okay? That's what this really means. So we read this. Probability of male, given Democrat. That means we've picked a Democrat. What's probably the person's male? I think a good way to think about conditional probability is that you're reducing the sample space. Okay? What we're saying now is we're not just looking at everyone in the survey. We're looking at just Democrats. And if you look at just the Democrats that were interviewed here, there's 60 of them. Okay? And then out of that 60, 47 were male. So that's the answer to this problem, 47 out of 60. Let's do another one. Let's ask for the probability where person was a female, given that we chose a Republican. So notice how I'm saying that. Probability the person was a female, given we chose a Republican. So now I'm reducing my sample space to just Republicans. So if I look up here, here's the column that says Republican right here. There are 40 of those, and 4 of them were females. So this is 4 out of 40. Okay. Let's turn that conditional probability around and see what happens. Okay, so this is saying that we've picked a female. What's the probability that person was a Republican? We read this, probably a Republican given we chose a female. You could say among the females if you want. All right, so now we're going to look at just the female column. So it's this column right here. There's 17 females that were interviewed, and we wanted to know how many of them were Republicans, so 4 out of 17. Okay. Notice how when I switch the conditional probability around, if I ask it in the opposite order, I don't get the same answer. You should not expect that. You should not expect them to be the same. Generally, they're different. Okay. Now, if you were to look in a common stat textbook and you looked for a definition or a formula for conditional probability, you would see something like this. And what they say is the probability Republican given female is equal to probability of Republican and female over probability female. Generally, whatever's in the second position becomes the denominator, and the intersection of the two sets goes in the numerator. Okay, let's use this formula in this problem and see what happens, and see if it matches this answer of 4 over 17. That's what it should do. All right, so let's go back to our chart. Probability of being a Republican and a female. Now, you notice in the numerator here, we're not saying given anything. So we just want the probability of being a Republican and a female. We go back up on the chart here. Probability of being a Republican or female is these four people here over the 100 people in the table. So that numerator becomes 4 out of 100 over the probability of being a female in this table of information here. Well, there's 17 females out of 100 people total interviewed. So that's going to be over 17 over 100 right here. Okay? So that's what the formula would tell you if you looked it up. And notice the 100s cancel, and you get 4 over 17, which is what we were expecting. All right. So another common question that often happens is, if you have two categorical variables, you might want to know if they're related somehow. So I might ask you something like this. I might say, is D Democrat and female independent? Okay? So we're sort of asking, is there some kind of relationship between party preference and gender? So I'm saying, are Democrat and female independent? All right, so we learned a test for that. Okay? D and F are independent if the probability of D and F equals the probability of D times the probability of F. So if that relationship holds, then D and F would be independent. So what we're going to do now is we're just going to check that. We're going to check and make sure that this relationship holds, or if it doesn't hold, we're going to say, oh, nope, they're dependent somehow. So let's find out. So let's find this thing on the left. The probability of D and F, we'll go back up to the table. Democrat and female would be 13 out of 100 people interviewed. So this probability on the left is 13 out of 100. And the question is, does that equal the probability of being a Democrat times the probability of being a female? Well, let's see. Probability of being a Democrat, there are 60 Democrats out of 100 people interviewed. So it's going to be 60 out of 100 times the probability of being female. I think there were 17. Yep, sure. 17 females out of 100. So here we go. We get 17 out of 100. And what we have to do now is multiply that and see if we get 13 out of 100. Because we know this side is really 0.13. So the question is, what does that side turn out to be? Okay, so this gives you 0.102. These things are not equal. Okay? So what does that tell us? It tells us that D and F are dependent. In other words, gender and political party preference have some kind of relationship. Now, you could even do a little better than this. You can make a comment about the relationship. So, for example, if you look at this probability on the right here, that's what we should have gotten if these two events were independent. So we should have expected about, this is basically saying the probability that someone was a Democrat and a female should have been about 10% if there's no effect on political party preference and gender, if they are not related to each other. But in reality, the actual probability was higher than that. Okay? So that seems to be saying that females are more likely to be Democrats than expected. Let's talk about a second way to test for independence. Okay? So this is test number one. This is one way to check. You do this thing. If they're equal, they're independent. If they're not equal, they're dependent. The second way to look at it is the following. If being female and being a Democrat are independent, then the following relationship should hold. Okay? So if D and F independent, then the probability of being female should equal the probability of being female given that I chose a Democrat. Let's think about that for a second. Ready? So probability of being female, that thing on the left, we're going to look at that. Probability of female there's 17 females out of 100. So here we go, out of 100 people interviewed, I guess. So 17 out of 100. And the question is, does that equal the probability of being female given I look at only Democrats? Okay? And again, the idea of independence is if they're really independent and I decide to look at just Democrats, the proportion that should be female should be the same. Shouldn't matter that I'm looking at just Democrats if being a Democrat has nothing to do with gender. So let's go look up here. If we look at just Democrats, there are 60 Democrats and 13 of them are female. So this is 13 out of 60. And the question is, are those two things equal? And they're not. You can convert them to decimals. All right, so this is 0.17. That's 0.22. And no, they must be dependent. Now, here's another fun thing, right? This sort of shows, again, that among Democrats, a higher proportion of them are females, right? Look, if we look at just the Democrat group, 22% of them are females. That's what this is telling me. Whereas if I look at the population as a whole, 17% were female, right? So what this is saying that if we look at just a group of Democrats, the females are taking a bigger proportion of that group, which means that these two variables are dependent. They're affecting each other. Challenge. Here's a fun challenge. Let's make a new chart here. Let's say, what was it? It was males, females, Democrats, Republicans. The goal here is going to be try and make a chart where the following is true. The probability of being female for the whole chart is the same thing as the probability of being female given Democrat. It's a worthwhile example. Try and do that, and then you'll see how independence works. All right, so in this table, the probability of being female would be all the females, there are 6 of them, out of the total table. Now, there's 3 here. Looks like there's 9 in total. Let's confirm that both ways. Here's 6, here's 3. Sure enough, yep. So this probability of being female, is 6 out of 9. Okay? And the probability of being female, given we're looking at just the Democrats. Well, if we look at just the Democrats, that's just this row, and 2 of them are female out of 3 possible Democrats. That works. That's what it means to be independent. All right, so switching gears, going with conditional probability, but a little bit further, so to do a slightly more advanced problem. All right, so let's consider the idea of HIV testing. Okay, and so let's just read a little bit. Okay, tests are used to screen blood specimens for the presence of antibodies to HIV, the virus that causes AIDS. Antibodies indicate the presence of the virus. The test is quite accurate, but not always correct. Here are some approximate probabilities for positive and negative of this particular test of outcomes when blood tested does and does not actually contain the antibodies. Okay? So we'll make a two-way table. Here's test results on the top. So you go in for a test, and they're testing to see if your body has the antibodies for the HIV virus. Okay? You can have one of 2 things happen. Okay? You can have a positive or a negative test result. Okay. Now, in reality, you can actually have the antibodies in your bloodstream. They can actually be present. Don't want that. Okay? Or the antibodies are absent or not present. Okay. So let's talk about this number right here, 0.9985. What is that telling us? That is telling us that if someone comes in and they have the antibodies in the blood, which means they've been exposed to the HIV virus, that this test is 99.85% likely to come back positive. Okay? That's what that's really saying. Okay? This is also possible. This is saying that 0.015% of the people who have antibodies get a negative result back. Okay? If we want, we can write that as a conditional probability. We can say the probability that you get a positive test result given that the antibodies are present is equal to 0.9985. Okay. Some other numbers that matter. Okay. It's also the case that sometimes people come in and get what's known as a false positive. And that category goes right here. This is the false positive people. Unfortunately, these people have been told that they have the antibodies in their bloodstream, but they really don't. So if someone comes in without antibodies present, there's still a 0.6% chance they'll be told that they do. Okay? And then that makes this number 994. That's the group, everybody, that you want to be in, right? This is saying that 99.4% of the people who do not have the antibodies in their blood, which means they haven't exposed to the antivirus, the HIV virus, are getting a negative result. Okay, so now, this is what we know about the test. Sometimes this number here is called the sensitivity of the test. So if you read in certain medical journals, the sensitivity test means how likely is it to detect what you want it to detect. All right? The question we're interested in is the following. We're interested in answering what's the probability that that the antibodies are present, okay, given that I tested positive. And we saw in the previous example that when you take a conditional probability and you turn it around, you don't always get the same answer. But if you think about it in practical terms or in real life, this is the probability that we're really interested in. This one right here. We want to know if we went and got a positive test result, how likely is it that we really have this antibody, that we had HIV? I'm going to re-express this. I'm just going to write a probability that we had HIV, that we really have it given that we tested positive. Okay? All right. One more fact that we're going to assume. So we're going to say, suppose that in a particular population, 1% of them carry HIV. Okay? All right, so let's get started. What we're going to do to answer this question is create a tree diagram. And then we'll label our conditional probabilities on a tree diagram, and you'll see how this works. All right, so we're going to start with the population. We can say 1% of them are carrying the virus. So we'll say here's the people who are carrying the virus. And the probability in this branch is 0.01. We could write that probability HIV equals 0.01. Okay. And that also means that this probability down here, probability 0.99, is not HIV. So if I put a little wiggly in front of this word, that means not. It's like from logic. Okay, so now what we're going to do is we start to fill in those probabilities that we had up here. We knew that if someone had HIV, that's this group right here, probably had a positive test result was 0.9985. So we're going to express that this way. We're going to say positive test result 0.9985, and then a negative test result 0.0015. Okay? This right here is that probability. This is the probability that we get a positive test result given we know the person is carrying the HIV virus. This is the probability of a negative test result given we know they carry the HIV virus. Okay. Down here on the bottom, 0.006 and 0.994. So there are some people who don't have HIV but are going to get a positive test result anyway, 0.006. That's the probability of a positive test result given the person does not have HIV. And then lastly, 0.994, here's the probability of getting a negative test result given we don't have HIV. Okay. So we want the probability of having HIV given that we tested positive. So you go and get a positive test result, and the question is, how likely is it that you have that you're carrying that virus? All right, so we know from our definitions that's really the probability of having HIV and testing positive over the probability of testing positive. We had shown that formula earlier as another way to calculate a conditional probability. Right here. Here it is. Right? We did the probability Republican given female, and we said we could write that as probability Republican and female over probability female, and we showed how to calculate that. So we're using that same formula in this new example. Okay, so here we are. All right, so probability of having HIV and testing positive, that is a particular part of our tree diagram. So if we look at our tree diagram, here it is. Here's the people that have HIV and test positive. So that branch. Okay, and to get that total probability, we would have to do 0.01 times this number here times this number. So this equals 0.01 times 0.9985. Okay? And then on the bottom, we've got to be careful, because the probability someone tests positive is not just that blue path through the tree diagram. There's another group of people who test positive down here. Those people. So you're either in one group or the other. You can't be in both. So we're going to add these two probabilities together. We're going to say 0.99 times 0.006. That's the probability of not having HIV and testing positive, right, in this population. And we're going to add that probability to the blue probability we got before. All right, so this is going to be 0.99 times 0.006 and plus the blue probability, 0.01 times 0.9985. And if you think about it, this denominator is sort of adding up the total proportion of the population who are going to get a positive test result. The first group are the people who actually have HIV. So this group here, these were people who had HIV and tested positive. So this is probability that they tested positive given, well, it's really this. We can write it this way. It's probability of having HIV times the probability of testing positive given we had HIV. And then this probability over here is the probability of not having HIV times the probability of testing positive given the person does not have HIV. Sometimes, if you look in some textbooks, this thing on the bottom is called the law of total probability. It'll often be in the same section of the book that mentions something called Bayes' theorem. Okay? This probability on the top is the probability of HIV, having HIV, times the probability of testing positive given we have HIV. All right, so now all we're going to do is type this probability into our calculator and see what we get. So if you type it in, you end up getting this answer, 0.627. Okay, so let's think about the meaning of that. What we're saying is that if you go and get a positive test result, there's a 62.7% chance that you have the virus. And I don't know how you feel about that. The probability is high, but it's not 0.9985. See, people mistake the sensitivity of the test for the accuracy of the test. Okay, this 0.9985 that I've circled here, this is how likely the test is to detect the HIV antibodies when they're actually in the body. Unfortunately, there's also this group of people which are told they have the antibodies and really don't. So that's what affects this conditional probability in the opposite order. When we turn a probability around, we can't expect the same answer. And what this is saying is that if you did get a positive test result, there's still almost a 38% chance that you're not carrying the HIV, not carrying the virus, or haven't been subjected to it.